Okay, so in this video, we're going to be reviewing an example problem of how to analyze the position of a 4-bar linkage using the position equations for a 4-bar linkage, which we derived in the last video and are now shown on the screen. So if you'll remember, theta 4 is the angle associated with the output link, and theta 3 is the angle associated with the coupler link. And what you may also remember is each of these equations, each of these solutions is of quadratic form, as denoted by the plus minus on each of them, meaning that for each input link angle theta 2 and for each set of link lengths A, B, C, and D, there are two valid solutions associated with both theta 4 and theta 3. What that means is each linkage has two configurations, an open configuration and a crossed configuration. And for any theta 2, A, B, C, and D, there is a valid theta 4 for the open configuration and a valid theta 4 for the cross configuration, and correspondingly, there's a valid theta 3 for the open configuration and there's a valid theta 3 for the crossed configuration. So let's go over a quick review of those two configurations now, and you can see those in this geometric diagram. Theta 4,1 is theta 4 associated with the open configuration, and theta 4,2 is the theta 4 associated with the crossed configuration. And in a similar manner, theta 3,1 is the theta 3 associated with the open configuration, and theta 3,2 is the theta 3 associated with the crossed configuration. Now, in the last video, we went into a deep dive on these two configurations and had a very in-depth discussion regarding the differences between the two and the mathematics to get to this point. So if you're interested, I'd encourage you to please review that video. But that being said, let's start with the example problem. So the first step is to come up with a theoretical linkage, and we've done that here. So we're going to analyze a theoretical linkage with an input link of length A, a coupler link of length B, an output link of length C, and a ground link of length D. And what we'll say then is A is equal to 2 inches, B is equal to 8 inches, C is equal to 6 inches, and D is equal to 10 inches. And this is just some arbitrary Grashof linkage. And if you're not familiar with the Grashof linkage, we will review that in a future video. But this is essentially just an arbitrary linkage. We're also going to assume that our input link has an angle theta 2 equal to 60 degrees. So now that we have this theoretical linkage defined by theta 2, A, B, C, and D, which is drawn to the right in the open configuration and drawn below that in the cross configuration, what we need to do is go back to the parent equations that we derived and then use that theta 2, A, B, C, and D to calculate all of these subparameters shown here, and then plug those subparameters into the parent equations and come up with our theta 4,12 and theta 3,12. And we will do that through use of a spreadsheet, and I will show that right now. Okay, so on this spreadsheet, you can actually see the theoretical linkage that we came up with on the notepad. And essentially, again, it is A is equal to 2 inches, B is equal to 8 inches, C is equal to 6 inches, D is equal to 10 inches, and theta 2 is equal to 60 degrees. And essentially what we've done is we've split the parent equations into their subparameters such that we have K1, K2, K3, K4, K5, and A through F. And this is a nice atomized way of approaching this problem, because what you can do is you can calculate one parameter at a time and then plug those parameters into a parent cell versus just having one cell that has all of these things combined into it, which would make for a little bit of a chaotic calculation. So here I just calculate one parameter at a time, and then I combine the parameters essentially one step at a time as we descend. So what you'll see here is we have our value cells, which is the first pass at the calculation. We have our units, so we are keeping track of what the units of our parameters are. And we have a check column, which is essentially independently re-putting in that formula such that you could check that you put it in correctly the first time. And this is obviously not necessary. It's just maybe good practice depending on what your application is. So what we have here then is we have our subparameters, again, K1 through K5 and A through F. And what we get from that is we then plug these subparameters into the parent equation, which we showed on the notepad, and you can see that we get our theta 4 open, our theta 4 crossed, our theta 3 open, and our theta 3 crossed. So essentially, with these inputs right here, what we're predicting is our theta 4 open is approximately 109.7 degrees, our theta 4 crossed is approximately negative 131.5 degrees, our theta 3 open is approximately 29.3 degrees, and our theta 3 crossed is approximately negative 51.1 degrees. So what this is saying is these theta 4 positions are saying this is where your output link should be in the open and cross configuration, and these theta 3 positions are saying this is where your coupler link should be in the open and cross configuration. So what we're going to try and do now is see if we can replicate these values in SolidWorks, and if we can, then we gain confidence that these equations are doing what we expect them to do. And of course, the advantage of a spreadsheet like this is if you end up just changing your values, your linkage, for instance, all of your values automatically update. So it's a nice parameterized way of doing this such that, the calculator can update as your linkage updates. And your linkage may need to update as you learn things about it and your design needs to change. So what we'll do now is we'll go into SolidWorks and see if we can replicate those initial values. And again, just for reference, A was 2, B was 8, C was 6, and D was 10, which we already have. Okay, so we will get into SolidWorks and see if we can replicate these values now. Okay, so here we are in SolidWorks, and what we have is a sketch with a few different configurations to represent the different configurations of the linkage, open and crossed. So to begin, let's just do a quick informal motion study of what our open configuration linkage looks like. So if we go into our sketch here, and we just start spinning our linkage, we can kind of get an idea for what the motion profile of this linkage actually is. So let's zoom out a little bit. And you can imagine that associated with this input link is maybe a servo motor or a stepper motor or a brushless DC motor or something such that you could crank this input link all the way around and it can make a full rotation relative to the other links because it's a Grashof linkage just like this. And this is how the linkage will move. And we would call this a crank rocker linkage, because this output link is rocking and we are cranking the input link such that it is making a full rotation relative to the other links. So essentially over its entire motion profile, the linkage will essentially just do this, and it can also go in reverse, okay? So now let's go to our configuration where we have the position equations solved in SolidWorks. So this is our fixed open, and we know what our angles should be, what we predict our angles to be. So using our position equations, we predict that our theta 3 should be approximately 29.3 degrees and our theta 4 should be approximately 109.7 degrees. So let's go into our sketch and see if we get that. So as you can see, with an input angle of 60 degrees, and we have A is 2 inches, B is 8 inches, C is 6 inches, and D is 10 inches, we do indeed get a coupler angle, as you can see here, relative to its local coordinate axes of 29.3 degrees as predicted, and we get an output link angle as relative to its local axes as shown here of 109.7 degrees, which we also predicted. So the coupler angle is 29.3 degrees and the output angle is 109.7 degrees, exactly as predicted by the position equations that we derived for this linkage for this theta 2. Okay, so the position equations were able to replicate the results from SolidWorks, in this case for the open configuration. Now what we'd like to do is see if we could also replicate the results for the cross configuration, which we'll show right now. So let's exit this sketch and change our configuration in SolidWorks. Let's go to the free cross and just kind of do an informal motion study of what this one looks like. So this is the cross configuration for the same linkage. Essentially, you're taking out this pin, disassembling this pin, and then reassembling the links in the only other position that they will reassemble at this theta 2. And it brings you from the open configuration to the cross configuration just like this. So let's go into this sketch. And now let's do a quick motion study here as well. So this is the cross configuration. It's just a different circuit of the same linkage. And as you can see, it is still a Grashof linkage. It can still make, the input link can still make a full rotation relative to the other links. But now you've kind of inverted it around or inverted it about the ground link. But in many ways, it is a very, very, very similar linkage. But this is now the other solution associated with the quadratic solutions of the parent equations that we saw earlier. So with that, let's see if we can replicate the results from the parent equation. So let's go to the last configuration here, fixed cross, and let's go into the sketch. So now let's see if we're getting the same results as our parent equations predict. So our parent equations predict that we should be getting a theta 3 of negative 51.1 degrees, which we are. So when we're going clockwise, our theta is negative, and when we're going counterclockwise, our theta is positive. So since we're going clockwise relative to our local coordinate axes. We're going clockwise 51.1 degrees. That is negative 51.1 degrees. So our equations have predicted that correctly. And then for theta 4, we should be going negative 131.5 degrees, which again, we're going clockwise 131.5 degrees relative to the local coordinate axes. So this is negative. This is negative 131.5. So negative 51.1 and negative 131.5. This is exactly what our parent equations predicted. So we are now again replicating the results for the cross configuration in SolidWorks as we predicted through our equations for a linkage of A 2 inches, B 8 inches, C 6 inches, and D 10 inches. Okay, so we have again proven that SolidWorks does replicate these position equations, which we would expect. And now we can go back to the notepad and have some final observations on the example problem here. Okay, so we've just shown that in SolidWorks we are replicating these answers properly. So we are indeed getting 29.3 degrees and 109.7 degrees for theta 3 open and theta 4 open respectively. And we are indeed getting negative 51.1 degrees and negative 131.5 degrees for theta 3 crossed and theta 4 crossed respectively. So again, you can see that theta 3 is positive for our counterclockwise, and theta 4 is positive for our counterclockwise, and theta 3 is negative for our clockwise, and theta 4 is negative for our clockwise. And here again is our open configuration, and here again is our cross configuration. Okay, so that was just a quick example problem to demonstrate the use of the 4-bar position equations. And in a future video, we will be doing the same for velocity, and eventually we will use that result to derive mechanical advantage and then start doing some dynamic analysis of these 4 bars. So that should probably be it for this video. I really appreciate you watching. Thank you very, very much, and I will see you next time.